Okay, in this lesson we'll be talking about applications of the kinematic equations or the constant acceleration equations. All right, so here are the four equations that we derived. A lot of people don't understand what equation to use when. It's really quite simple. If you look at this first equation, you have the final velocity, the initial velocity, acceleration, and time. Obviously, you cannot use that equation if you're looking for displacement. The only thing you can do in that first equation is find one of the unknowns if you know the other three. Let's look at the second equation. We know the displacement, we know the initial velocity, the final velocity, and the time. We can't use that one if we don't know the acceleration. And once again, you'd be searching for one of the unknowns if you know the other three. And the same thing is true with any of the other equations. The same process can be gone through. Okay, we need to show all your work when we do problems. This is a basic idea of how to solve all problems in physics class. You need to write down the given. This may be shown as a sketch. A lot of times sketches help you understand what's going on a little bit more than just throwing down numbers. You want to try to explain what is required, what you're looking for in other words, and then solve it. This would be a written explanation as well as equations with units and numbers and answers, the math. Don't be afraid to write down some words in your solution to explain what you're doing. And don't skip steps. If you do, I'll be writing TAMO on your papers. And what TAMO means is then a miracle occurs. I love this cartoon. Okay, let's look at some reasoning strategies for this type of problem. You want to make a drawing. Decide which directions you want to call positive and which to be negative. It's completely up to you, but once you make the decision, you have to kind of stick with it. Write down the values that you know and what you want to know. And then when you pick out one of the equations, when you're going through your ideas of what equation to use, you have to actually pick one that you know at least three of the variables. And sometimes some of these problems are divided into segments. And at the ending, say, speed of one segment will be the beginning speed of the next. So you got to keep that in mind. And that's a situation where it might be a good idea to write down some words to explain what you're doing, just not math. And finally, keep in mind that there may be two possible answers in kinematic equations. This has to do with the idea of something being squared, which you'll see in one of the examples to follow. All right, so here's one of the examples that we'll be going over, and we'll be doing many more in class. This is just to give you an idea. What is the displacement in the following problem? In this case, you were given the initial velocity. You don't know the final velocity. You know the acceleration, and you know the starting and ending times. So this is the information that was given to you. And what you want is the final position. All right, so we need to pick one of our kinematic equations to solve for the final position. I chose this one because we knew the initial speed, we knew the time, we knew the acceleration. So we're able to solve for the displacement directly from this equation. Putting the numbers in, you can see that 6 meters per second times 8 seconds. The seconds cancel out and you're left in meters, which is correct for displacement. And then you have 1/2 2 meters per second squared times 8 seconds squared. The seconds squared cancels out with the seconds squared here, and you're left with meters, and ends up being 110 meters. Now I just wanted to point out the fact that in this particular case, the acceleration and the initial velocity are in the same direction. They don't necessarily have to be. Some common math mistakes with using this equation is people tend to square more than just a t. But if you remember in the derivation, the only thing that's squared is a t. Okay, let's try another one. A spacecraft is traveling with a velocity of 3,250 meters per second. Suddenly the retro rockets are fired and the spaceship begins to slow down with an acceleration whose magnitude is 10 meters per second squared. What is the velocity of the spacecraft when the displacement is 215 kilometers relative to the point where the retro rockets began to fire? Okay, your book tends to give information in this format, and I find it very helpful actually. It's listing the 5 kinematic equations, variables you can possibly have. Time is not given, but it's looking for v. And here's the other 3. Notice the acceleration is negative, and the reason is because in the problem it says you're slowing down. So if this is a positive velocity, then if you're slowing down, this must be negative, acting in the opposite direction. All right. So, what equation should we use? Well, we have to use an equation that doesn't have t in it because we have no information on t. So we're going to use this one. And we're going to solve it for the final velocity. Now the final velocity is equal to the square root of v initial squared plus 2ax. There's actually 2 answers that are given in this though. It's plus or minus, okay? Because this velocity could end up having a positive or negative value due to the square root. And take a moment to look at the math, make sure you understand it. If you need to pause, go ahead. All right, so let me try to explain this positive and negative again. Sorry about the bird clock in the background. Okay, one of the answers was a positive 2,500 meters per second. This occurred as the retro rockets first were fired. It slowed this down to 2,500 meters per second. But there's actually another answer that makes sense as well, which I'll show you now. This continued slowing down, and it eventually came to a stop. If the retro rockets kept on firing, it would actually go back the opposite way. Both these answers, 2,500 meters per second and negative 2,500 meters per second, occur at a displacement of 215 kilometers. So that's why sometimes you have 2 answers for a problem.